Because one thing is too big a page to leave blank. That is just a representation of an atom and those things going around, and you really cannot see in real life. It's like a fan that's turned on. You know the blades are whirring because you feel the wind coming off of them, but you can't see the blades until you take a picture and freeze the action. Well, that's frozen action, but in real life, those electrons are moving so fast, you can't see them. You just know they're there. Okay. Well, here's the first one. This should, I've underlined the blanks. Go ahead and fill them in first, and I'll come back and talk about them. And I'm hoping that my screen perfectly matches what yours is. And those are my words, of course. I mean, you can find where it says, else they are no longer what, you know. But I want to tell you what I mean. Sometimes I use red, sometimes I use different, I always underline the missing word. And I make a different colored font, different colored text. And I brought this in. You're going to need one of these probably. There are many on the internet. This is the one that I call my favorite. It tells you the name of the atom. It tells you the oxidation numbers. It tells you so much good stuff. I've never seen one yet that tells you this much. And so, if I'm not mistaken, I think on the lessons area I had my own. Or you can print it yourself. It comes as a PDF form. But you can go online and find it and download it, which is what I've done. I just cut the step out of it and you can go right to it. But there are other ones that are prettier. They've got all kind of colors. But you soon learn the colors are just pretty. They don't do a whole lot for it. I need the information that this has on it. So, and you're going to learn how to operate this thing, how to use it. Because, see, I'm a biologist, I'm not a chemist, but I can use this. So things that biologists do, a lot of folks said, I know I taught biology in the other class, the other kind, and they went, ain't this chemistry? I said, yeah, it sure is. And biology people know it. So we got to get it too. But anyway, these are elements. These are the elements. And there's one atom per element, and one tells you that. And if you take an atom, I use oxygen, and you split that sucker down, then you lost oxygen. All these things are made of protons. They're all made of electrons, and they're all made of neutrons. The trick is how many protons. Because if you're number one, you're hydrogen, you have one proton. If you're number two, you're helium, you have two protons. If I add a proton to helium, magically it turns to lithium, which is 3 protons. If I add another proton to get 4, he turns to beryllium. It's just like magic. The number of protons is what you are. And if you have 8 protons, you're going to be oxygen. If I add one more to you to make 9, then magically you become fluorine. That's how this works. And matter of fact, if you look down here at gold, which is not Go, gold is number 79. It's called Au. You know what it's not called Go for? Because in Latin, gold is called aureum. And these are symbols. They're not abbreviations. They're symbols. And the symbol for gold is Au because the folks who first discovered it spoke Latin. And they said, this is Au. We say gold. And sodium is not So. It is Na because in Latin, sodium, the word is medium. So you can't go with the idea that these are abbreviations. That would make no sense then. If you abbreviate a word, you use a letter, don't you? So when I say abbreviation, I'm wrong. These are symbols. They're atomic symbols. You always write the first letter capital. You never write the second letter capital. Because if you did, then you would find some problems with how you read this. If you look at number, I know you can't see it, but on mine, 27 is cobalt. Big C, small o. If you in your haste to write cobalt wrote down big C, big O, that ain't cobalt. That's carbon monoxide. And big C is carbon, big O is oxygen. And if you just simply made this, just a mistake, I didn't mean to do that, it's a bad mistake. Big C, big O is not cobalt. Big C, small o is cobalt, because that's a symbol. But in that case, CO is actually, it matches the thing pretty well, CO is cobalt. Silver is Ag. Same reason, because the Latin word is not the word silver. Some are named for people: Einsteinium, Lawrencium, Madame Curie is Curie. We have all kinds of ways of naming these things. And sometimes we know when to discover it. Sometimes it's been like gold. There's no discovery date for gold. It's been here for eons. But oxygen was discovered back in the 1800s. First time ever. And then we breathed it for eons. So if I take oxygen and I break it down into its electrons, protons, neutrons, I just lost oxygen. If I take the eight protons and say, I want 4 and I want 4, then I've got 2 carbon atoms. Because 4 is carbon. Now, I think, no, 4 is beryllium, 6 is carbon. But the main thing is, you can't get below the atom. You can, but you lose the structure, you lose the element. And that's what A means on there. I can break it down further, but I no longer have what I had before I started. This ring here, of course, is gold. And I can break it and chop it and chop it and chop it and chop it, smaller pieces, smaller pieces, smaller pieces. It'll be gold, right? Well, I get that single atom. Can you see it with your eye? Too small. I can break that single atom into protons and electrons, but I've lost the gold. I no longer have gold anymore. So as long as you have an atom, it's gold. But this ring is not pure gold. Better not be. You know what better not be for? It'd be too soft. You can bend it all up. So they add an alloy to it, silver or aluminum. And whether it's 14 karat, 10 karat, it's how much gold it is. Because you may have seen the old westerns, they got to take a gold coin and bite it. He wants to see teeth print. He sees no teeth print, that ain't gold. And that's why they stopped using gold in currency. That's filthy. I don't want to pocket something that you bid on and other folks have bid on. Of course, you don't buy it on a nickel or a quarter because you can't bid it anyway. All right, so anyway, first slide is basically over. It's about elements. And this thing here says 118. But we even stopped naming them. We're saying that if we find one more behind 109, we're going to call it that. I can't say that, but that's the Latin word, like Roman numerals. That's the Latin word for 101. 100 or 110. And there's some charts where you find that 107, borium, is not called borium. We have just named borium. This is cutting edge. We just named borium. So it's no longer some 3-letter thing. So atoms are the components of elements. You can't go smaller than an element. Well, you can go, but you lose the element. So that's the smallest thing you have. The next slide is about these particles that make up an atom. Subatomic because they are smaller than the atom. Sub can mean under, like a submarine under the ocean. Sub can also mean smaller. In this case, it means smaller. I would say this slide you probably learned in high school, if you remember that far back. I taught it in high school. That's how I say I thought you may have learned it then. The three subatomics are electrons, protons, neutrons. The order is not important how you say them. It's just how I happen to do it. The arrangement there is from smallest to biggest. I didn't mean to, but that is from smallest of the electron to the biggest of the neutron. But the neutron, beside the proton, you wouldn't tell how big it really is. They're almost identical size. It's just a shade bigger. Electrons are very, very tiny, and they have a negative charge. Have you been shot with electricity before? And you feel electrons. Pure, that's what electrons are. These lights right here, they work because electrons flow through them. That's how it works. The light in your house, the incandescent light, works because electrons flow to the wire, and the wire gets real hot and glows. And that's the light you see. You ever try to change a light bulb that just burned out? Yeah. Burn your fingers. You gotta get your cotton or kitchen mitt. These don't get hot. There's a gas in those, and it's also nice that the room is kind of hot sometimes, and those incandescent bulbs, you could stand it. It's also kind of smoother light. As you look around, it's like evenly lit up. If I had light bulbs, there'd be a bright light here, and a bright light here, and a bright light there, so it makes it pretty nice to have these fluorescent lights. Protons compared to electrons, huge. You can put 1,835 electrons in one proton. How big is an electron? We're talking about tiny. I don't know a word that fits it. Tiny, minuscule. Because an electron is one, if you use a fraction, it'd be 1,835th the size of a proton. But get this, as far as charge goes, the electron is just as powerful as that proton is. Proton ain't much to brag about, really. If he's that much bigger, he should be a lot stronger, but he's not. And thank God for you electrons aren't as big as protons, because that little shock you got would have fried your brain like the electric chair does. It takes a whole lot of electrons to kill you. That's the amperage. I mean, you can take the little batteries in your tongue and touch it. It won't kill you. That's how it takes them for how much charge is in them. Good thing they're not powerful. So the electron, it ain't just smaller than a proton. It ain't comparable. It's so small. But to me, the fact that the charge of an electron equals the charge of a proton tells you either protons are really sorry or electrons are really strong. So that's how it works out. The next one, neutrons. What's neutral mean?
No charge.
They have no charge at all. They have no charge at all. But a lot of folks, I give it 10. I understand this. I'll say proton, what's the charge? And they say positive. And I'll say electron, what's the charge? And they'll say neutral. And then for the neutron, they'll say negative. You know what they're doing, don't you? They're matching the ends up. They haven't learned it. They're matching ends up. They're saying, well, N, negative, N, neutron. That must, you can't match them like that. Electrons counter protons. If you have 10 protons in an atom, you will have 10 electrons. Because atoms have no charge. If you had 10 protons and just 5 electrons, what do you have more of? You have 10 protons, 5 electrons. What do you have more of? Protons. How many more? That atom would have a charge of +5. When they're all born, on this chart here, when they're all born, they're nothing. For example, if you look at oxygen, which is number 8, he has 8 protons. He will have 8 electrons, guaranteed. But now if he were to gain too many electrons and have 10 then, what's he have too many of? He still got his 8 protons, but now he's got 10 electrons. What's he have more of? How many more? 2. And what's their charge? Well, that atom that I gave electrons to is they're called an ion. And it's a -2 ion. An atom is an ion that has had something happen to its electrons. Now, if you had like 8 protons and 8 electrons, and I took away 2 electrons, now you got 8 versus 6. What do you have more of then? Protons. And what's their charge? How many do you have? You have 2 extra, right? So that ion would be a +2 ion. Now, did you get to be +2 by adding 2 protons, or was it by taking away 2 electrons? You never can add protons, because if you do, you lose what you have. If I want an ion of oxygen, and I add protons, what happens to oxygen? I lose oxygen. It becomes something over here called neon. So to make an ion of oxygen, I have one choice. I got to fool with the electrons, because if you mess with the protons, that number 8 for oxygen, you mess that number up and you lose your oxygen. So you can never bother protons. You can only fool with the electrons. I say I mean nature does that. When you set fire to paper and the paper burns, the oxygen in the air is reacting with this cellulose and giving off energy, which you see as light. It also burns you, right? Now, will things burn in the absence of oxygen? No, because there's no reaction. I got to react oxygen in the air. Now, question. Here's paper. There's oxygen. Why don't it burst into flames? Why don't it just burst into flames? Everything's ready. Everything's here I need. I got to provide the energy, right? To start the reaction, and a match does that. I light the match. There's your energy. The moment it starts to burn, the reaction starts to occur. Now, when the oxygen's all gone, I still got a paper, what's the fire do? It goes out. It goes out. And the match I use is called startup energy. Now, can you use friction to start a fire?
Yeah.
Yeah, you know you can. If I get it hot enough,
Stone, you rub two stones together, yeah.
A magnifying glass off the sun, shine down, make a little point, it'll start smoking for long. And when I get it hot enough, the reaction starts by itself. In your attic, can you have fire up there? How hot's getting your attic? Yeah. If you have, say you're saving old newspapers from the time you're in college and they're up in the attic, you can have a fire up there like that. Just because it got so blame hot. I have fans in my attic that come on and suck out the hot air. It's still hot up there. I think the biggest thing, I don't know why you have it for, is oily rags. Oily rags. The oil lowers the reaction required. I don't need a match for that. It'll start by itself. Friction can start that. So, electrons, like I said, I could put that many electrons, 1,800 or something, into one proton. Electrons are real little bitty, but they're just as powerful. The next slide comes up is about the neutron. The third subatomic is the neutron. They're just a little bit heavier than the proton, not much. They have no charge. That's what they call neutrons. They're neutral. And that last sentence tells you why it's just a bit heavier. And everything in 3E I've told you already. Somewhere on your paper, write down this. 1 proton equals. 1 proton equals. And then say 1. And then say AMU in small letters. AMU. 1 proton equals 1 AMU. And right below that say 1 electron equals. And then go back for a minute. See that number there, that 1,000 number? Mm-hmm. Say 1 over that number. Like saying 1/10, say 1 over that number. Equals 1,835th AMU. Now, look at that. How many of those electrons will it take to make one whole proton? 1,000 numbers. 1,000 numbers. I just told y'all. In one proton, there are 1,835 of those, because that's equals one, that fraction. Now, add those two together and what do you get? Add those two together and what do you get?
1.1.
1.1835. That's how big a neutron is. Now say this. One neutron equals, and then add those two together, that's a neutron. 1 point, that number. Now, compare that one of the proton to the neutron. Is that a lot bigger? I mean, it's just a tad, right? If you have one, and that's a proton, and you have 1.1835 neutron, is that like a whopping big one?
No.
But is it bigger?
Yes.
Could you even see it probably?
No.
That's why I tell you, the neutron next to a proton, they look alike. But in real life, because a neutron is a proton, electron glued to it. See, all a neutron is, you take a proton, take an electron, plus negative, stick it together, plus negative cancel, right? They cancel, becomes nothing, right? Well, that conglomeration of those two, we then call a neutron. Well, really all it is a proton glued to an electron, and that's why it's just a tad bigger, the 0.1835, than the proton is. But you won't know that by looking, you can't tell that. But we know it's a fact. So the neutron is just a little bit bigger, because it is nothing more than a proton and an electron glued together. It has no charge, because the plus in the proton cancels the negative in the electron. But that's no charge, yes.
Okay, so basically one electron is basically 1 divided by sign over 1835 AMU, and the neutron is 1 times?
1 point. You add them together.
Wait.
If I have one proton plus that 0.1835, that becomes the sum 1 point.
Oh, okay.
You're not multiplying.
0.01831?
1.1835.
Oh.
That's the weight of the neutron. 1 point. I add it together. If you have $1 and you have 50 cent piece, ain't that 1.5? I didn't multiply one
I thought we were
time.
timesing it.
If you multiply, you'll get that same 0.135 number, whatever the thing is. You got to add them together, because on here they're stuck together. They're added up. So an atom is composed of 3 things, but it's the protons that makes the difference. On this chart here, all these numbers on top, they're called atomic numbers. That's the number of protons. And if you look across there, they line up beautifully. And you start over again. Kind of like your calendar, you know, you go through 7 days, right? You start over again. Is that not periodic? This goes over, a lot more than 7, starts over again. That's why this is called the periodic table, because it starts over. And all the members right here, all these members, like, that would be Sunday, right, on my chart, on my calendar. Sunday or Monday? No, it'd be Sunday. Well, all of these have the same properties. All of these, if you put water on these, they burst in flames. You say, water puts fire out? Not all the time. These things are so reactive, they react with the oxygen in the water. So if you have a factory on fire, and you plug in your fire truck, but first find out what's in that factory being stored there. Because if it's sodium, and you put water on there, you made it worse than it was when you got there. Now, this paper on fire, yeah, water put it right out. But this ain't sodium. In high school, I brought in, myself and Joe Skinner were only 2 teachers who were allowed to have sodium because it was so deadly. And as you move down this table, they get more deadly. Sodium's one I use. And I always carry a knife in high school, not technical stuff, because I'm using the lab. And sodium, it reminds me of like ivory soap. It's kind of solid like that. and you put on gloves, because even the water in your fingers, it'll burn your fingers up. You put on gloves, and then you can handle it then. Take your knife and cut off the smallest piece you can get off, the small bit. Now I took a petri dish, which is a glass dish, right? I don't use plastic, I use glass. I had an overhead projector back then that had a light shine through it, right? Go to the screen. I put that on my projector. And I'm teaching the class about the reactability of sodium, and I take that knife and just flick that little bitty sliver, and then flames start shooting up out of the thing, and it starts foaming, the water gets boiling hot. And they go, that's when they really realized when I said that water and sodium reacts violently. And then they said, Mr. Jeff, you got any francium? Shoot, no, I got francium. It blow me up. So lithium does that also, but lithium's not quite as sparkly. Potassium, we have potassium at Hardaway, but I didn't use it. I always use sodium because I can control. And one guy said, put the whole block in there. You're a fool. And you see what a little sliver did? And that's how, when you go to Toys R Us and buy a chemistry set, there's some things you don't get in that set. One of them is not sodium. Because kids start mixing things together. So I guarantee what's in the chemistry set are all going to be basically tame. When you get to college chemistry, and they got those vents in the rooms, and the professor tells you don't mix them, he ain't joking to you. You start making mistakes. And that's why in high school, my kids never touched it. Because they don't listen. They don't listen. If they hurt themselves, I'd be the one soon. So I always did demonstrations. And they always sit back, ooh and hard. They want to blow the bathroom up one time. Wonder what happened if I put that sodium in the commode. It ain't going down the commode. It's going to react right there on the water. So it won't blow it off. You might lose your hair. So oxygen, carbons, name any you want to on here. They're all determined by the number of protons they have. There's a number on top. And the number on top is that number of protons they have. And a thing we call chemistry. In the old days, lead's pretty heavy, right? I fish with lead. Well, gold's pretty heavy too. And of course, lead ain't worth nothing. Gold's worth, everything you think of. The old kings thought, man, I could make my kingdom richer if I took all this lead I have and changed it to gold. And all his wise men, his scientists, his people like that, he says, I got a project for y'all. Why don't you take this lead, you do what you got to do, wave your wand over it, and change it to gold. Oh man, they studied, they looked, and they zapped, and they fired, they burned. Everything. They never did get it to turn to gold. But they did come up with a science called alchemy. And now we call it chemistry. Nothing more than man's greed is what led to the science of chemistry right now. Of course, greed does cause wars too anyway, so man's greed is a major motivator, as you know. Are you here because you're greedy and want to make more money? I guess somebody you are. Nothing wrong with that though, is it? No. I call it ambition. Some call it greed. It's ambition to me. If you ever get a chance to take a college class that you can just audit and not have to take any tests, you'll enjoy it thoroughly. The pressure's off. You can walk out with what you want. That's the best kind to have. But you get nothing for it either. No piece of paper that can done it. But anyway, let's do a next slide here for us. That ain't even close to a proton next to an electron, is it? So that electron, maybe about 6 the size of that proton. If I were to put a period on there, just a period, that might be closer to the size of the electron next to a proton. What I have up there is hydrogen. I know it's hydrogen because there is just one proton. And if you have one, you're always hydrogen. And I said symbol is H. Again, that's not an abbreviation. It looks like it is, but it's not. It's a symbol. And you must always write big H. Yes, ma'am?
Abbreviation is one of the fill in the blanks.
Oh, it is? I didn't do it? Well, thank you. I can fix that. I didn't know. So that should be read too, correct?
Yes, sir.
Good. I appreciate you doing that. Just that part of it?
We have to.
And let me get the E also. Any more problems before I get at it?
No.
On 4A, you have opposite electrical charges attract.
All right, should these be read?
Opposite and electrical should be.
This should be read right here. Okay. So those two should be read. That work? Any other problems y'all see right now? Oh, good. I didn't know that. And I'm glad y'all saw it. Okay, you're the first one to see the PowerPoint. You know what? I made it up and showed y'all. All right, good. You do know the opposite attract, right? Well, that'd be physics or chemistry. Opposite attract, that'd be physics or chemistry. That's physics. That's physics. Is that true in marriage?
Sometimes.
Sometimes.
It's like more like a common enemy.
Yeah. I mean, I reckon if you're both headstrong, then you have a lot of fights, aren't you? Someone's got to be prepared to compromise and give in to make it work. Let's see that. Are you married? Are you married?
I was in a relationship that was like
Okay.
that when we put it.
And you're both butting heads. Then you're the same charges. So that won't work then.
Peace.
Two positives, but now in my family, I got to admit though, in my wife and I, she's more serious than me. I'm a little more laid back. She works numbers better than me. Now I couldn't bounce check half time. So hey, I got checks. I said I got money in the bank. Ain't what it works, is it? I know in our marriage, when our sons, the only fights we ever had in marriage was how to raise little boys. No financial problems, no fights because of that. She would say to me, "We shouldn't let Robbie climb that tree out there. He may fall out and hurt himself." But that's Mama.
But
I'm saying that's how he learns, baby.
he'll learn not to climb.
He'll learn by, and if he don't grab that limb just right or test that limb and falls out. Well, she goes, "But you want to hurt yourself?" "I don't want to hurt yourself. But I know this is going to happen. He's going to do it one way or another.
He needs to.
Rather do it in my house, I can watch him, than off in the woods by himself,
Before he breaks his arm.
where he gets hurt and nobody can see him." So, as a matter of fact, I had an oak tree, and my family used to have tree service. And I was a climber. I climbed trees using ropes and those spikes on your feet. And Robbie, he only did it. And I'm scared of him do it. I recall my mama could never watch my brother climb because fears going to fall out. I bought an old rope home, and he took and threw it over a limb, and he tied it to his belt. You see, when I climb, I have a saddle we wear, a real saddle. And then the climbing knot we tie, which you go around, you got the rope a long tail, you go around this thing twice, cinch it, and then the knot will hold you up. And you pull a knot down, you'll come down, they're going to knot, it'll stop you. And you can swing around the tree, as long as you don't touch that knot, you're fine. Well, I never sure how to tie that knot, but he was watching. And my friend Roger one time, I said, "Roger, don't teach him this knot, because he'll be out somewhere." And Roger did, of course, but Roger likes to be friends. And I watched him out in the climbing tree. It was a big oak tree, big to him, small to me. He took the rope and threw it a limb. And I watched him do it. I said, And I saw him, he was looking at it, and I knocked on the window at the den. I said, "Come here, my wife." And we picked around the corner of the house. I said, "Watch this." "What's he doing?" He said, "You're going to climb that tree." "Oh, stop. No, leave him alone. So he got that rope tied over the limb and tied down to his belt right here. He began to pull. And he'd forgotten that ain't the way we do it. We tie the knot. And when I got on the ground below me, he's pulling too. So when I let go, I don't fall, right? Because the guy behind me on the ground's got the rope. You'd think that'd be pretty simple, but not for Rob. He got there and he kept pulling, and his belly went up first, and now he's laying like this. And it dawned on him, he can't tie that knot. He was trying to tie a knot, and his hand loose, and he fell. He didn't fall this far. Hit the ground, there's a root down there. Across his back. His mom wouldn't run to him. I said, "Don't you go, don't you dare." He looked around, nobody saw him. He pulled that rope down that tree, threw it down and stomped off. Now, if she seen Mama looking at him, he'd done what?
Crying.
He'd cried. He know Mama would come and give him comfort.
Pick him up.
And, it wasn't until a little while later on that I said, hey, Rob, you seen that rope? Yeah, it's up there by the tree. I said, what are you doing? I said, trying to tie it. So I tried to tie a knot there. He goes, oh, that's how you do it. And then he didn't want to anymore. It's like wet paint. When you say don't do it. So I said, well, go and time it now. And he decided he didn't want to try it. But I told the wife, though, I'd rather him do it there so I can watch him fall. If I got to take him 911, I'll be there for him. But he's going to try it. You know that?
Yeah.
So why make him sneak off somewhere and do it when he get hurt and no one see him? Boys, and I have a girl. I have no daughters. Thank God I got 4 nieces.
Lucky.
I'm around their finger. I know I am. They run up and bob around. I love to try to do it for them. But opposites in my house is me and my wife. We're together on some things. We both value education. We both value time alone together. But there's some things that we have different opinions on.
That's
I
right.
mean, I love to hunt. She can actually care less. She's not against it, but she doesn't care. She loves fishing though, but she won't bait the hook. That makes me mad. If you're going to fish, you do everything. But yeah, we're opposite in the house. Basically, all the housework and all the furniture buying, she does that. I don't care. White couch is like this, Bobby. To me, they look like I don't care.
If I can sit on it, it's a couch.
But you know, she goes, sit on this one, and I will. And I can tell a lot of times about when she keeps grabbing back to one she likes. Once I figure that out, I go, I like that better. And she smiles. I got to figure it out sometimes. I tell you when the class started, electron is not still. It's not stationary. It's always moving around the atom. Actually, it circles the nucleus. Let me ask you a question about that word nucleus. In a cell, is the nucleus always dead center?
No.
Can be on the side?
Yeah.
In an atom, it's always dead center. In an atom, the nucleus is always dead center, but in your cells, it can be anywhere. On the edge, in the middle. And some of your cells don't even have a nucleus. Your red blood cells, they got nucleus. Because it did all the oxygen. Nuclei love to eat oxygen. Well, your red blood cells carry oxygen. If they had a nucleus, it might be cooking cookies. I cook a dozen, you might get one. I get a dozen of them myself. And that'd be a nucleus, because I'd eat them all before you got there. The electron being negative, is it being drawn to the proton or pushed away? What do you think? Protons are positive, electrons are negative. Is it being drawn toward the proton or shoved away by force?
It's drawn. Opposite.
It's being drawn.
Yeah, opposite attract.
Why do they crash in? The satellites, your cell phones, and your GPS work on satellites in space, right? They're moving, right? If they move too fast, what's going to happen? So they don't. If they move too slow, what's going to happen?
It's going to fall down there.
Crash. Watch the trick.
Perfect speed.
Go just fast enough that you don't leave the orbit and you don't get sucked back to Earth. That's that force, that electron. Electrons go just fast enough to not leave the atom, but at the same time, too fast to be drawn back to the nucleus. Now, where do you think you're going to find the greater attraction? Electrons near the nucleus or electrons far from the nucleus? Greater attraction.
There.
Oh yeah, the nearer you are, the faster you better go. And in photosynthesis, where the sunlight hits that green plant, right? And the green plant uses that sunlight to make energy, to make food. The electrons in the chlorophyll, when the sunlight hits them, they jump out to a farther orbit. Well, here they have a lot of energy, here they have not many. The energy that they lose is used to make food. So when the light hits the chlorophyll, the electrons move to a further orbit, they go slower. All this energy right here that you just lost is now made to make sugarcane. Now, the electron must be replaced So it can do it again, right? And then you got two photo systems. One of them uses sunlight, and one of them does not use sunlight. They both happen in their daytime. Photosystem 1 uses sunlight, photo 2 does not use sunlight, but they don't happen in dark. Plants, you breathe out carbon dioxide, right? They breathe in carbon dioxide, and they also take in water. What we give off, they need, and what they give off, we need. We're a perfect partnership. So the force of the electron is kind of like us going around the sun. We go just fast enough to not fly off into space, but fast enough the sun don't suck us into it. And a meteor or a comet coming, it has a shape like this. Because it is pulled to the sun, goes by the sun, then gets pulled back, and it's fired back. It's always going to be elliptical. Our orbit's not that way. Right now we're in summertime, right? Are we far from the sun or near to the sun? Near. No, we're far. Hotter it gets, farther we get away from the sun. That makes sense to y'all? Wintertime we're real close to the sun. You think we should burn up, right? It's the way the Earth sits on an angle, right? And as it goes around the sun, the angle changes, right? Right now, our angle is such that, yes, we're close to the sun, but the sun's rays are bouncing off of us. As you move closer to the sun, like, see, this is, we're starting to move closer. So as we move closer, wintertime comes. As you move farther, summertime comes. And still, some folks say, I don't understand that. I would think that if I stand close to a fire, I'm getting warmer on it. If I'm back from the fire, I get cooler, right? But you do know that if you stand by the sun, by a fire, this place gets real hot, right? How about your back?
It stays cold.
You got to turn around, don't you? Well, the way it is for us in the earth, as you get near the sun, we slant away from the sun. So that we're close to it, the sun's rays are bouncing off of us, and we're at wintertime. As we back from the sun, we start to face the sun more. And we're farther from it, where we're standing we're right dead at it, and the sun hits us and sinks in. So though we're far from the sun, we're getting all the sunlight and none's being reflected. That's summertime when you're far from the sun. Now, boy, thank God it ain't backwards. Because if you got close and turned to face it too, ocean would boil away. That's the most amazing thing to me when I first figured it out. And if we worry about atomic explosions changing that tilt of the earth, and thinking the weather is changing, yeah? We don't know whether change is something nature does by herself or something we've caused. We don't know that yet. But we're having record highs, record lows. So I don't know if we can hurt the earth. We can't hurt the earth's ability to have life on it. You can't destroy the planet, but you can destroy whether we can hold life or not. I mean, if your house fills full of poison gas, can your house support life? Can you destroy the structure? It's still there. House still there, but it can't support it. So we can't destroy the earth. We cannot destroy the earth. But we can destroy the earth's ability to support life. And that's one we're worried about now, now some folks say that just to get more money. They make you afraid so you can pay more money. And some folks say that's hogwash, that we're not getting another ice age, nothing like that nature at all. Frankly, I don't know. All right. The atoms are small. Oh boy, those are exponents. See, this is 5 times 10 to the negative 8. What's MM stand for? Millimeter. Wish I had a dime. Anybody got a dime? Somebody hold a dime up. Somebody hold a dime up. I want to show you something about it. Anyone got a dime? Okay, put it between your fingers. Put it flat between your fingers.
Like flat?
Yeah, flat. How much space is that dime taking up from your fingers? A foot? No. An inch? No. 1 millimeter. That space, how thick that dime is 1 millimeter. That's a fact. So, this mm means how thick that dime is. Now, you see that -8? On that 5, where's your decimal really? In front or behind the 5? Really behind it. You see the negative sign for the 8? That means move the decimal 8 times this way. If you take that decimal place and go 1, 2, 3, 4, 5, it becomes 0 and then 7 zeros and that 5. If I took that dime she had and I sliced it, I can't even say that number. That thin, 5 of them would be how thick an atom is. You can't see that. I don't know. I know that -6 would be a million. That might be 100 million there. 500 millions. If you took that dime and sliced it to 100 million slices, could you see one of them? Ain't no way you see one of them. 5 of them, though, would be how big an atom is. That's what that means. So now, if I said 5 times 10 to the 8th power, I move the decimal the other direction. And so it becomes 5, then 50, and then 500, and then 5,000, and then it gets bigger. So the exponent, if you see a negative, to me it's pointing to the left, and that's where I move the decimal. If I don't see anything, then I move it to the right. And that's how. And that's what I'm telling you there. Oh yeah, I said that's 10 million, 10 millions. That's awful small. There's no way you can see one atom. You can't see 2 atoms. I can't see 3 atoms. And there's a dime thing I showed you there. And if you imagine your finger hold that dime, 20 million hydrogens could go across that gap. 20 million. I can't see it that small. I can't see one of them. But that's how small these things are we're talking about. Have we ever seen an atom? No. We just play games with it. For example, how do you know the wind is blowing? I see it. Outside there, I know there's wind. How do I know? I see trees blowing. I see evidence, right? Now, could a squirrel be in a tree running around making that thing shake?
Maybe.
I could be wrong, right? I mean, I can't see the whole tree, but what I see there is moving, so I assume there's no squirrel up there somewhere doing that the wind must be blowing. Well, these things here, we assume certain things because we see evidence of them. And that's how, but we've never, ever seen an atom. But everything we have on here, everything we do proves they're there because it works. I was in a class at Auburn, and the professor was talking about how big these things were. And I never forgot, he said this. He said that if you want to think about how big an atom is, think about the Georgia Dome. I've been there, I've seen the Georgia Dome. He said, out there on the 50-yard line, in the very middle of it, put a BB out there. Could you see it from sitting in the vision? No. He said, that BB will be the nucleus. And the dome itself, or the electron, are going around it. That's big. That's big. And the nucleus is still minuscule compared to the atom. And that's why it's over here. You know, a kilometer is a little more than half a mile. And to scale, you're talking about half a kilometer. That's about 3/10 of a mile. But if you think about a BB out there, I'm saying that guy was pretty close. So in the world of the atom, which is minute, right? Those electrons are still very, very far from that nucleus. Everything we're talking about is just so small you can't even see them with your eyes. All right? If I don't blink, it's still better than write the whole thing, ain't it? Plus you get the whole gist of it. That first one there, that number 2 under 5B, about what's a billiard ball? You know what it is, don't you? It's a pool ball. I thought about the billiard is pool, right? And of course you hit them and they hit, you can ricochet off, right? Well, there's no way 2 pool balls can go in that corner pocket at the same time, right? They're too big. Protons and neutrons, they're not bouncing off each other. They're not bouncing off each other. But when you rack them, like you rack it, and you have that triangular rack, they're in there, aren't they? And protons, now think about this, protons all have a positive charge. 8 protons stuck in that tiny, tiny nucleus. Are they trying to be together or trying to fly apart?
They're trying to fly apart.
They're trying to fly apart. They got the same charge. They don't like each other. They're trying to fly apart. What happens when, say my 2 sons get in a fight, and I step between them? Stop! This proton and this proton are trying to nail each other. I'm a neutron saying separate. So what I've done? I push these 2 protons apart so that their attraction is not so strong anymore. And you look at these bigger things down here, the numbers get very big, but the protons are really outweighed by the neutrons. Because the neutrons get inside there and shut them apart so that there's no conflict. When you get above 83, you become deadly. On this chart here, when you get above 83, you become what we call radioactive. And that means that you have so many protons and so many neutrons that the nucleus is still unstable. And now and then something flies out of the nucleus. And that thing flies out of it, that's radiation. And how good is that to us? Take it. It's also X-rays. Now X-rays is radiation. But do they warn you about being X-rayed too much?
Mm-hmm.
Oh yeah. And if you're an X-ray technician, they warn you about taking too many shots of it. They put a little badge on you up here. When that badge turns a certain color, then that's when you got to stay home for a little while. I know because my sister-in-law is a radio technician, and she works in Atlanta. And one day she made a mistake. She took her badge off, but she put it in her pocket. And then she washed her lab coat. The fluorescence in the detergent turned the badge. She's in her car going to work and just put it back on and not looked at it. She walked in, they freaked out. Hey, you've been exposed. She goes, I just got here. Come find out she had washed her badge. Of course, they all reacted like they're supposed to react because it's been turned naturally. You ever hear of Madame Curie?
Mm-hmm.
She's the one who discovered plutonium. She discovered the radium. She died from the poisoning. Her husband died from the poisoning. Her daughter died from the poisoning. The very thing they were handling that was so fascinating was uranium. Do you handle uranium like that? We now know not to. Back then they didn't know that. She didn't know this. It's invisible. But she got leukemia, a cancer caused by exposure to radiation. And Rosalind Franklin, that lady who had discovered DNA, the guys who discovered DNA, they were using models. She was using X-ray photography. And they just said, she would get real mad when they said, you can't come to lab for a few days because you've been exposed to it. She died at 37, ovarian cancer, caused by her X-rays. She died before they gave credit to her for her role in the Nobel Prize. Watson, Crick, and Francis all won the prize. Matter of fact, Francis wrote a book. He called her names because he thought a lady's place was at home pregnant, not in a laboratory. And when she went to King's College, they had separate rooms for men, scientists, and lady scientists. She's the only lady there. So when you got together to discuss ideas, she wasn't allowed in the room with them. And her boss, Maurice Wilkins, took her picture without her knowledge, and he gave that picture to James Watson. And James Watson says, oh, this is it. This is, I mean, look at it. And so James Watson, using her picture without her knowledge, discovered how DNA was put together. She was there. She died. She worked up to 2 weeks before her death, and she died. They won the Nobel Prize in '62, and nowhere was she mentioned as even a part of it. Now we look back and see that she was a major part of it. Without her picture, they'd still be looking from her. And then she became friends with Francis Crick, but she never did. Matter of fact, they said at one time that they called her Rosie to her back, and she didn't like Rosie. But she was going to punch out Watson. They had to get twin, like me and my two sons. Rosalind Franklin was a real smart lady. And I don't know why she didn't speak up and say, hey, wait a minute. I think one thing she didn't know the trick. Her boss gave a picture away without her knowledge. But that's a movie now. It'll make you madder and I'll spit how they did her. And I read his book. And at the very last page he says, other folks have read this book and their remember might be better than mine, but there's one person I need to say I'm sorry to, and that's Rosalind Franklin. He said, I didn't realize the turmoil, the prejudice that a smart woman has. And even though he said that, I still think he's a dog. I still don't like him.
How come you don't
He's still living. He's still living. And he hates blacks.
No.
He is really prejudiced. And he lost his great job. He no longer is invited to speaking tours. He is a smart man with some real problems.
But sometimes hate clouds your conscience, though.
The book is called The Double Helix. It's called The Double Helix. And it's soft cover. And it's about that thick. I mean, I just got to read it about 2 weeks ago. And it's a good book to read. But all through the book, the first time they put them all together, they told Maurice Watkins and Francis come look at it, the lady, she goes, that won't work. She was rude too. That's stupid. He had all the bonds on the outside. She thought the bonds went inside where they do. But he had arranged where all the bases on the outside sticking out. She goes, that won't work. So a year later, he tried it again and didn't invite her back because she didn't want to be criticized by her, that woman again. And so when he saw that picture that she had taken with her special camera that he got without her permission, he then knew the structure of DNA. And what we're teaching right now is what he discovered back in '52. I was 2 years old then. Don't remember myself. But Rosalind Franklin is a lady who was really done dirty. Really done dirty. And she died because of her own X-ray photography. When she exposed to X-rays, they got her too. So she died at 37. No telling what she would have contributed as she lived to be like 80 or 90. It's the most amazing story I've ever read. Oh, if you buy that book though, one thing, Francis, his partner, and Maurice would not sign off on it. You spoke so bad about Rosalind Franklin. They would not say, they wouldn't sign off.
They wouldn't sign to
They
the
would not-
apology
they would
or
not sign off that. And the original publisher in London would not publish it. So Doubleday did instead. It became a bestseller overnight.
Wow.
And all that stuff in there about Rosalind Franklin, I think it's the biggest bunch of crap you ever saw. But the only guy who looks good in the whole book is Watson. According to him, Francis Crick was a buffoon. And Francis Crick was the man who was working on it when Watson showed up. Watson was a young kid on the block. He was like 23. Know-it-all. Oh, he was terrible.
Who wrote the book?
James Watson did. It's his autobiography, a discovery of. And there's like, no, I didn't. When I read it, I said, this is true, this is true. Some things he said in that book just wasn't right. And Linus Pauling was also trying to find DNA answer. And Watson was fighting to get there first. He would do anything to get there first. It was an ego problem. And he was taking people's data and using it for his own. But the biggest injustice was done to Rosalind Franklin. And they called her Rosie to her back. So she was a very straight-laced lady, and her name was Rosalind, but they called her Rosie. In his book, he called her Rosie. But in his last page where he talks about he did her wrong, it's Rosalind then, all the way through. But I figured, she's dead and gone, and no one knew about that. Her best friend, another writer, was the one who blew the whistle on him. He wouldn't say a thing about it. But she knew what Rosalind had done, and what he had done, and that's, boy, it hit the fan then, buddy. And this very day, the new books, I don't know if your book discusses Rosalind Franklin or not. By God, it should, though. But she is a major contributor to the discovery of DNA. And I hope now they give her fair shake. I'm going to say something about this bottom line. I didn't get here enough. You know that electrons are moving. They just never stop, right? They're all directions. And it's more like a light beam where I shine the beam and I can shine the particles flow through. You see the particle, right? You ever seen light come through your house and how dusty your house really is? All the dust floating in, you go, my God, look at the dust! And then you look at your table and go, no, I know where it comes from now. As you walk around your house, you stir it up. But sometimes the beam will come through the window just right. And you see dust floating through the beam. And it amazes me to see how much dust is in that house. And my AC filter, I know why now, but once a month I better change that sucker. It's sucking air through there, and that dust is going through there too. So, but the electrons are not at all like a billiard ball. They're more like a wave, like a light wave, and they never stop. So the idea of actually spinning, it's just in and out, in and out, in and out, always moving. Now, so many people are so used to drawing the Bohr model, which is circles of electrons around the nucleus. That picture on there is what we would say right now represents the electron cloud. Do you see where it's the darkest part of that blurry cloud? That's where it spends most of the time. You see on the outer edges is real light? It's out there too sometimes. You see inside where it's lighted in? It's in there sometimes. But where it spends most of its time is where it's darkest. And it's moving. It forms a blur, like a people's wheels on their car. And that little cross in there is a plus, because the nucleus is plus. Protons plus neutrons equals plus, because neutrons are nothing, right? And that blurry cloud out there, if I put a charge in it, what charge would it be? What electrons? They'd be a negative. If I put a charge out there, and I almost did when I made the slide, I said, oh, wait, I'll just see if they can figure it out. I know that that nucleus is plus. That's where the protons are. And that cloud would represent negative. Now, if it speeds up, it will get further from the nucleus, right? It slows down, it's closer to the nucleus. But there's a range in there that's real dark where it spends most of its time. But you never know where it actually is and one time to the next. Like a fan blur. You feel the wind, but you don't know where they're at. I threw the word out nuclei. Give us a nuclei and nucleus. What's the only difference?
It's plural.
Plural and singular. Nucleus means one. Nuclei means a bunch. It's just a singular plural. And for the sake of teaching it, we're going to pretend it's a spinning particle, even though it's blurred. We're going to think you can see it, and you can stop action and look at it. And I told you earlier that you always have as many protons as you have electrons, because they got to have the same numbers to kill each other, to be neutral. And that's what number 7 is saying too. If I got 7 protons and 7 neutrons, 7 electrons, there's no overall charge. Because 7 pluses kill 7 minuses. An atom has no charge because they're always equal numbers. And hydrogen, of course, is the smallest. Only got 1 proton. And because of that, it's got 1 electron. So plus 1, negative 1 equals what? Nothing. So an atom is always nothing. All these on here are atoms. If you see 83 on top of it, that's 83 protons. What do you know is a given then? You've also got 83 electrons. Because 83 pluses plus 83 negatives gives you nothing. All these things are nothing. So when I say 99 on top of this thing, I am telling you 2 things. 99 protons, also 99 electrons. I ain't got to say it twice, do I? There's something you need to know about the charge. And one thing you know is that all these atoms have no charge. Therefore, if you have 5 protons to have no charge, you must have 5 electrons too. And the number tells you the number of protons, and then you know the other number because you realize that they're equal to each other. And uranium is number 92, somewhere over there. 92 tells you uranium has 92 protons, and the atom also has 92 electrons. Now, if I lose some electrons, is it still charged, plus there's still no charge then? No. If I lose electrons, there's no longer balance. If I lost electrons, I have too many protons then, it becomes positive. If you give me electrons, and I have too many of those, then I become negative. And all I'm doing is, I've changed the balance of my protons to my electrons. Anyone thinking of the most common atom in your body? I know water is the most common compound. What's the most common atom? What do you have more of? Hydrogen, oxygen, nitrogen, sodium?
And
Oxygen. There's more oxygen than anything else. And half of it's because you get so much water. All right, number 8. Helium, second simplest, it's got 2 protons. And see where it says He? That's not he. That's helium. This right here, I'm not referring to him or her. He, I'm saying helium has 2. I wish I had done something to make that more clear. But that right there is not he has 2. Helium has 2. Kasha wrote the word out. But a lot of folks think I'm talking about him as the atom. Helium has 2 protons in its nucleus. Therefore, it has 2 electrons also. But helium is the one that has a neutron. You don't find neutron. How many protons are in hydrogen? Can one kid get in a fight with himself? I don't need to get in a duel. If you got 2 heliums, 2 kids, you might be there between them, right? So the first time you see a neutron is when you have 2 protons, and they might be banging heads, so a neutron in between and say, y'all knock out. You don't need one for a hydrogen because you only got 1 kid unless he's psycho, he ain't gonna fight with himself. So you don't need neutron for hydrogen. But for helium, you got 2 protons, and they don't like each other. So they have a neutron between them, keep them apart. That's why I said with the helium, you introduce a 3rd particle, that neutron. And the more protons you got out, the more peacekeepers like neutrons you got out too. Because if not for that, then the nucleus would just fly apart. The atomic bomb, we make that happen. Albert Einstein was a German Jew who lived in Germany just prior to Hitler's arrival. Hitler was doing what to Jews?
Killing them.
Killing. What did Einstein do?
Ran.
He fled. Thank God he fled. Because he fled to America and couldn't speak a bit of English and learned over here on the street. Einstein went and talked to Roosevelt and said, I want to show you something. He didn't know who Einstein was. Just some weird looking dude. I want to show you something. And he tried to explain to the president atomic theory. How'd that go over? Not too good. So, but he got enough to Roosevelt. Roosevelt says, what's this guy talking about? And he called in his science advisors. And Einstein told them what he was thinking about. All this energy in the nucleus that's trying to get apart. He says, I've got a way to make it get apart. And when energy is released, it's tremendous. That's the atomic bomb. The Manhattan Project was one that he worked on. And all Einstein's idea. And all the simple thing was this. Einstein said that if I can make a collision, here is plutonium, here's plutonium. If I take and make a bullet out of this one, and I fire this bullet like from a gun, bang, into this one, it'll start a chain reaction. That chain reaction gives off this heat. It'll melt concrete, it is so hot. That's it. And when they dropped that first bomb on Japan, it blew up 1,000 feet up in the air. It never hit the ground. The reaction started up there. And you saw the mushroom cloud come up. People didn't know what hit them. They didn't suffer at all, except on the outskirts. The concrete just melted like wax. Remember how hot that is to melt like wax? That first bomb was only like 15 kilos. It would have 15,000 tons of dynamite. Now we got one, but that's not like a firecracker. But Einstein, and you know Francis Crick. I'll tell you about Francis Crick with the DNA. He was also in the Manhattan Project, and when he saw it, he resigned from the Manhattan Project and began to work on DNA. He was so distraught by the death and devastation. He says, "I can't believe I did this." So watching Francis Watson resigned from that project. That's how smart that man was. And Enrique Fermi, who led the project, he goes, I wish we never opened this can of worms. We can't put it back in that can. We dropped 2 bombs. We only made 3. We made 3 bombs. Oh, I thought we had that before. They said, let's bring Japan over here and show this thing blow up. And show them what we can do to them. And Einstein goes, no. What happens if you push the button and nothing happens? They're going to think you just fooled. So Einstein was one that shot down there and no, we're going to drop. So we tested one bomb. We dropped one bomb in the United States ourselves. We nuked ourselves first. It went off on a. You ever seen the firefighter towers that they sit and they look across the country? We had a tower built like that, bombs up there. It went off.
In New Mexico.
It was just devastating. They flew over Japan, dropped out leaflets to Hiroshima saying, evacuate the city. We've got a bomb coming that you ain't gonna imagine. Of course, they didn't believe us. We were bombing them every day. That one bomb dropped off and killed hundreds of thousands of people. And we kill civilians. Now, civilians can run the government. They say one of the worst. The Japanese army had never, ever lost a war. Never lost a war. They weren't going to quit.
They don't give up.
We invaded Okinawa, which is to them their land. We lost. Oh man! So we said, well, we got to invade Japan. It's going to be such a loss of life. So Truman was the one that says, drop the bomb. Show them what we got. We dropped the bomb on Hiroshima. People says, quit. Army says, no. Emperor's undecided. So we dropped our last bomb. We planned to put on Tokyo. But clouds covered over Tokyo. So we couldn't drop it there. I kind of think that might be divine intervention. So we went down the coast to Nagasaki, another seaport town. We dropped it there instead. That thing went off there, and they said, we quit. Because they didn't want to do an unconditional surrender. They want to have conditions. We said, no, you have no conditions. We'll tell you what's going to be like from this point on. And the battleship Missouri in Tokyo Bay, they came to us. We made them crawl out there and sign that thing. MacArthur signed it. The problem was Russia learned about the bomb. Like Patton said, we need to turn right around and take care of Russia. We didn't. So I grew up afraid of the bomb. That Russia's one day going to, Khrushchev told us he's going to bury us. I heard that, I heard on the radio, he said, my daddy got fighting mad. Khrushchev, I'm going to bury you in America. My father built a bomb shelter in our house. Go into it, became a fort later on. But man, we were scared. And the idea, they taught us, and I think, Fort Benning is not a target. It's a training center, it's not a target. Fort Bragg, where I was. They said, if they're coming to bomb us, you get under your desk, put your head between your legs, and one guy said, and kiss your butt goodbye. That's what we're going to boil down to. Thank God no one ever did punch that button. Because we're all afraid that we do mutual annihilation. It all began though right here though in 52 when Einstein came along with this stuff. And Einstein, he never was sorry for it. He never was sorry for it. But Fermi and other ones were going, what have we done? But now we use power to make electricity though, so it's not bad. We use it for good too. Ships, nuclear power. We change crews, put some more food on them. You got to gas it up. We don't run on gas. It's nuclear power. It boils water. And the water spins the propellers. It'll boil water forever. Time's up. We come in tomorrow, and I'll probably be showing this slide. Because I always show my last one, I move forward. Next time y'all give me a sign, so I know. I don't want to go past 145.
Now, the pop quizzes that you're going to end up giving us, are there?
There's no pop quiz till I finish this.
Okay.
Then it comes.
Okay.
It'll come the next day. If I finish it tomorrow in 5 minutes, I won't do a pop quiz that same day. It'll be the next day I see you.
Okay.